I'm happy to be presenting at LIAG seminar once again. I think after 2 years, 2 years ago, I think was the last time that I presented here. So let me first share my screen. So I hope now you can see my presentation.
Great.
So let me choose also the laser. As Hartwig mentioned, I was working at LIAG at the project play type, where I was evaluating how faults were evolving both spatially and temporally in the Molasse Basin. The work that I will be presenting today has been carried out as part of my PhD project that I started back in 2019 at LIAG. And basically, the slides that I will be presenting today showing basically an update of my PhD thesis that I accomplished after having left LIAG and started working at the Geological Survey of North Rhine-Westphalia. So today I will be talking about geometrical evolution of normal faults in the German Molasse Basin with a specific focus on mechanical stratigraphy and the structural inheritance. So the general idea of my PhD project is to investigate how normal faults in the foreland basin settings evolve spatially and temporally, and what factors define this evolution. In order to understand or gain a better understanding into this complex topic, I chose as my playground the German Molasse Basin, which is part of the North Alpine Foreland Basin, which is fairly well covered by 3D seismic data. And using this seismic data, I carried out a thorough fault analysis in order to get a better understanding of how faults evolve in this kind of settings. So here you see a figure that shows the Bavarian Molasse Basin, which is part of the German Molasse Basin. And these traces are basically the faults that are imaged at the top of the Malm Reservoir from the Geothermal Atlas of Bavaria. And here we can observe an overall fault pattern, which is characterized by normal faults that strike parallel to the alpine origin. And these are so-called flexure-induced faults that resulted in response to the foreland flexuring due to the orogenic loading. Within the distal foredeep, which is this area on this illustration, the vertical stresses superseded the horizontal stresses, whereby the minimum horizontal stress attained the orientation which is perpendicular to the basin axis and parallel to the thrust propagation. So as a result, in the distal foredeep, we've got formation of normal faults that strike parallel to the alpine origin. But while the lithospheric flexure is the primary mechanism for the development of normal faults in the foreland basins, local specifics, such as, for example, what I already mentioned, mechanical heterogeneity of the sedimentary sequence and pre-existing faults, can exert a major control on the geometry of the individual faults. And this is something that I recognized while working on my first 3D seismic data set when I was still at LIAG. It was a 3D survey acquired in the southern part of the German Molasse Basin, approximately 40 kilometers south of Munich, around the area of Gerrit Street. And here I observed a quite interesting fault pattern, fault configuration, which is illustrated on this representative seismic section that runs north-south across the 3D survey. So here we've got two fault arrays that are geometrically decoupled from one another. We have in the lower stratigraphic sequence an array that consists of normal faults that offset Mesozoic and the earliest most molasse sediments. And then above, across this gray layer, which is represented by incompetent Rupelian clay marls, we've got an upper fault array that consists of normal and reverse faults. Having analyzed fault displacements and growth strata, I was able to establish, first of all, timing of the faulting. The lower fault array originated during the flexural bending in the Rupelian. Then there was a period of tectonic quiescence, and this was followed by a renewed activation of faulting, whereby faults of the upper fault array nucleated in competent Baustein beds, which are represented here by the orange layer, and they propagated both, they grew both by upward and downward propagation. Then there was a third stage of reactivation as alpine thrust propagated further northward onto the foreland basin, and the faults that were optimally oriented to the tectonic stress regime were reactivated as reverse faulting, as reverse faults. And it seems that the presence of a thick clay-dominated layer, which is this one, most probably inhibited the downward propagation of the upper faults and their eventual linkage to the lower faults. Considering the orientation of the upper faults with respect to the lower faults, which is more or less collinear, we can assume that the lower faults served as kinematic attractors to the nucleation of the upper faults. So based on this study, we can see that mechanical stratigraphy, in this case, the influence, the presence of thick clay-dominated marls, as well as structural inheritance, which is represented by pre-existing lower fault array, influenced the geometric evolution and the overall fault pattern in this region. And with this model of temporary evolution of the faults and hypothesis on how mechanical layering and pre-existing faults influence the faulting geometry, I moved further northward geographically to the area of Munich, and I wanted to see how this model of temporary evolution and hypothesis on how mechanical stratigraphy and pre-existing faulting influence the fault geometry correspond to the fault geometries that we observe in this region. And here I had two 3D seismic surveys at my disposal. One is a GRAME 3D cube and another one Unterhaching 3D survey. These 3D data sets have already been interpreted by former LIAG colleagues, Ewald Lüschen for the case of Unterhaching and Jennifer Zisch for the case of GRAME. And those interpretations were taken into account in my fault analysis. So in order to observe the fault pattern, I here show you two maps that were extracted from these 3D surveys. On the left-hand side, we see an attribute, multi-attribute map, which is basically a core renderance of variance and curvature attributes. And on the right-hand side, we see a two-way travel structure map. And these both correspond to top Preabonian, and top Preabonian is basically top of the Lithospheric limestones. These are limestones that accumulated during the early molasse sediments in the Eocene, and this is basically this horizon, and it represents the strongest reflector across the Molasse Basin, which is basically then the interface between the earliest most molasse sediments below and the incompetent clay marls above. So this horizon served as a quite good base to interpret the fault pattern. So what we see on the multi-attribute map are the fault traces, and we can clearly recognize three major fault systems. One is fault Nymphenburg, then we've got fault Munich, and then to the southeast we've got a quite complex system of faults, whereby this fault is considered to be a master fault as it accumulated the larger displacement. This is fault Otterbrunn, and basically on the two-way time structure map, we can see my interpretation of faults. And if we now lay a cross section across the two surveys, we see the following fault configuration in vertical sections. We see here on the left-hand side fault Nymphenburg. We see both branches of fault Munich represented as through-going faults, so they displace both Mesozoic and tertiary stratigraphy. They show no vertical segmentation, whereas here on the right-hand side we see a quite similar fault configuration to the one that we saw at Garrett Street. We've got lower faults that are geometrically decoupled from the upper faults, and this fault segment and this fault segment are interpreted as fault segments of fault Otterbrunn that I mentioned previously. If we look now at a different cross section that was laid orthogonal to the strike of the fault Otterbrunn, this one more to the northeast, represented here, we see that at this cross section there is no vertical decoupling along the fault trace. We see here through-going fault. And as we move along strike to southwest, we see that basically the fault bifurcates into two vertically separated segments that have a distinct lateral offset. So here we observe a long strike variation in geometric coupling between the deeper structural level, which is represented by top Preabonian, and the shallow structural level, which is represented by top Chettian. Another interesting feature that fault Otterbrunn system possess is that unlike fault Munich or fault Nymphenburg, it is not oriented parallel to the strike to the extent of the alpine origin or to the basin axis, but rather in an oblique direction, basically south northeast to southwest. So to me, that was a quite interesting structure to observe. So in order to understand how it evolved geometrically and temporally, I looked at the throw distribution and stratal thicknesses, how they vary across it. And here, once again, we've got the cross-section orthogonal to the strike of the fault Otterbrunn C. And on the right-hand side, we've got two graphs, one representing the throw values that I picked along at around 21 horizons that I was able to correlate across fault Ottobrunn, plotted against depth. So that's this graph. And then we've got so-called fault expansion indices, which are basically a measure of stratigraphic expansion across faults and are defined as a ratio of hanging wall thickness to footwall thickness. And the fault expansion indices that have a value of 1 or more than 1 basically show a thin sedimentary faulting. Here we see that the values are above 1 for 3 intervals, Cretaceous interval, Rupelian interval, and also to some extent during the Aquitanian. And now if we look at the shape of the throw depth profile, we see that within the Cretaceous, within the Rupelian interval, and also within the latest Chettian and earliest Aquitanian sediments, it has a quite negative slope, negative gradient. So we have a quite a drastic decrease in throw values, which is indicative of thin sedimentary faulting. So what we recognize here is that this fault was active during at least 3 stages during the Cretaceous, Rupelian, and sometime during the late Chettian and early Aquitanian. And at least 2 stages are they correlate well with the observations that I made in at Garrett Street, where we also had fault activity during the Rupelian and Chettian. And in order to see to what extent these observations are valid along the fault, I also looked at the thickness maps of the respective intervals, and here we basically also see thickening of the hanging walls across fault Ottobrunn, which is indicative of the fault activity during the sedimentation of this package. Here, for example, we've got a thickness map of the Cretaceous interval. The warmer colors represent thickening of the interval. Cooler colors represent thinning. And if we look at the fault Ottobrunn, we see that across the fault, especially in this region, we have sedimentary depot center, which is indicative of the fact that sedimentation was active as sedimentation was taking place as the fault was active. We also see thickening across the fault for the Rupelian interval and also for the Aquitanian interval. So basically now we postulate that there are 3 phases of faulting activity. That's our temporal constraints. So what about the fault evolution in terms of spatial evolution, in terms of geometric evolution? For this, I looked at the throw distribution along fault, which is represented by this figure. So basically, I picked throw values at 21 displaced horizons. And I did that with an interval of around 250 meters. And then I projected the throw values onto a vertical plane along strike of the Ottobrunn fault. And then I constructed the contour maps. And that was, this figure is basically a result of this process. And here it is important to note that I was able to do this high resolution throw mapping only for this portion of the fault, which was covered by the, which was imaged by the GRAME survey. This was not possible for this portion of the fault, which is imaged by Unterhaching, because of some resolution constraints within this survey. Yeah, so what do we see here? We see a quite distinctive pattern. We have throw maxima below top Preabonian, and then we have throw maxima within the Chattian sediments. It is postulated that the areas of maximum displacement are usually representative of the loci of fault nucleation. So I postulate that the fault most probably first initiated below top Preabonian, most probably within the Upper Jurassic Carbonate sequence. Then there was a period of tectonic crescents, and then a new fault segment above within the competent Chattian layers nucleated. And here in this region we see throw minima. This corresponds to the Rupelian marls. Here the idea is that this basically fault segment propagated both upward and downward, and this downward propagation, downward deformation was accommodated by ductile deformation within the clay marls, and therefore here we have throw minima. Yeah, and this is this scenario is quite coherent also with the observations that we did at Garrett Street. There we also have two segments that are decoupled from one another. Here we see a coherent fault trace. So here the upper fault segment managed to coalesce with the lower segment. So I mentioned that there is an along strike variation in fault coupling, and this can be illustrated by this figure. So what we see here, it's an overlay of fault traces from the deep structural level, which is represented by top Preabonian, and these are color-coded as gray. For example, this one for the master fault of the Ottobrunn system, and also the traces at the shallow level, colored either as blue traces, and blue represents the fault portions that are coupled with the below lying fault segments, and then we've got orange segments which represent segments that are not coupled with the beneath lying layers, beneath lying segments, fault segments. What is interesting is if we look at the throw distance plot for the Ottobrunn fault, here we've got basically the throw values that are plotted against distance along the fault. As gray are the throw values at the deepest, at the deep level, top Preabonian, and the blue curve, blue profile are the throw values at top Chattian. And we see that the portion of the fault which is characterized by coupled fault segments, we see on the throw distance plot that it's basically the area or the portion of the fault where we've got the highest displacements at top Preabonian. And as we go towards southwest, where we see decoupling of the upper fault segment to the lower fault segment, we see also the decrease of the fault displacement at top Preabonian, likewise to the northeast. Another interesting observation is that the throw distance profile at top Chetian more or less mimics the geometry of the throw distance plot at top Preabonian, whereas somewhere from here it does not anymore. So it seems like in this portion of the fault there the kinematic dependence of the below-lying segment to the above-lying segment dissipated. If we also look once again here at this figure, another interesting observation is that the lateral offset between the gray trace and the color trace increases to the south west, and also the northeastern tip of the fault at the upper level curves to adopt a more west-east orientation. So let's just keep these observations in mind and see how this correlate with the overall growth history of the fault. Oh yeah, this is something that I forgot also that I will be mentioning. If we look a bit closer to this northeastern tip of the fault in 3D. So as turquoise, I've got the fault plane, and that's a fault Ottobrunn, which here, for example, we have this decoupled segment that is then below coupled with the fault Ottobrunn antithetic and oppositely deeping fault. And as yellow polygons, these are the cutoff lines of top Preabonian at the deep level, and red polygons are cutoff lines of top Chetian. And we see if we compare the average strike direction of the fault segments at deep and shallow levels, we see on average on the Ross diagram a clockwise rotation of 20 to 30 degrees. So now I'm coming to basically a growth scenario for the Ottobrunn fault. As I mentioned, we've got here a sedimentary depot center observed at the thickness map of the Cretaceous interval, which is indicative of the fact that fault Ottobrunn was active during the pre-orogenic stage of the foreland basin evolution, during the passive margin phase in the Cretaceous, and the extension was most probably taking place due to the opening of the Penninic Ocean to the southeast. And therefore, we here recognize, or we can see this oblique orientation of the fault, which is quite untypical to the faults that we observe elsewhere in the Molasse Basin. So then, during the flexural extension of the foreland basin during the early orogenic times, this Cretaceous fault most probably got obliquely reactivated. The fact, or the proposition that it was obliquely reactivated is supported by the fact that at the hanging wall of the master fault, we've got an echelon faulting and also horsetail splays. And these are indicative of a strike-slip component in faulting. Yeah, and then there was a period of tectonic quiescence, and in the Chetian or in the Aquitanian, a new fault segment nucleated in the within the Chatian interval, and most probably the lower segment served as a sort of kinematic attractor to this nucleation. Then within the central part of the fault Ottobrunn, the upper segment nucleated, and here it is proposed that the largest structures that have largest displacement, they are more likely to localize strain. And this is most probably where the upper segment initially nucleated, then it grew by upward and downward propagation and also by lateral propagation. And eventually it coalesced with the lower segment, forming a coherent through-going fault. But then, as the fault, the upper fault segment grew laterally to the southwestward direction and to the southeastward direction, most probably this kinematic attraction dissipated, and the fault trace started to evolve more independently, kinematically independent from the below-lying fault. Therefore, we have here the increase of the offset between the lower fault segment and the upper fault segment, decoupling. And in the northeastern part of the fault, we've got a curvature of the tip of the fault in order to adopt a more optimal west-east orientation with respect to the regional stresses, as during the flexural extension, the orientation of the minimum horizontal stress was more or less north-south oriented. Yeah, so that's basically a gross scenario of the Ottobrunn fault, and with this I come to a summary of my observations, basically on both areas that I analyzed in the south at Geretsried and also in the central part of the German Molasse Basin around Munich. So in the German Molasse Basin, we recognize faults that formed not only during the flexural extension, during the early orogenic times of the basin formation, but also during the pre-orogenic stage, during the passive margin stage, represented by the Ottobrunn fault. Then during the flexural extension itself, the faults evolved in two stages. So we see an intermittent faulting, with the first stage taking place during the Rupelian, which was then followed by a period of tectonic quiescence, and then reactivation of the faults and during the Chattian or Aquitanian. And in Geretsried, we see that it already happened in the Chattian. In the central part, most likely during the Aquitanian, and this correlates well with the northward propagation of the alpine thrusts. So we see the younging of the fault activity towards north. And the Chattian and Aquitanian upper fault segments most probably nucleated initially geometrically decoupled from the stratigraphically lower segments, and whereby the pre-existing faults, such as the lower faults, they served as sort of kinematic attractors for the nucleation of the new fault segments. And the key role in the final geometric pattern played the Rupelian clay marls, which serve as a mechanical barrier to the deep linkage that accommodate displacement by ductile deformation. And we see, well, the Rupelian clay marls, they thicken towards southeast, and around the area of Geretsried we have quite thick Rupelian clay marls, and there we do not observe the coalescence of the upper segments to the lower segments, which we do observe in the central part of the German Molasse Basin. Yes, so with this, I have come to an end of my presentation. Yeah, and if there are any questions, I will be happy to answer them.